Hello, few familiar faces. Thanks a lot, Jose, for the previous talk. He actually covered a few things that I was going to cover anyway, so thank you. Well, really? um, but anyway, so today we are going to go through should I upgrade my Java. Ideally, this is a 10-second presentation where I just say yes, and then all of us go get some nice beverages of that we like. But generally, we all like to see data and understand the why behind the yes. So let's look at it like real quick. I'm Nikhil Nanivadekar. I'm one of the active project leads of an open source collections framework. It's called Eclipse Collections. The other active project lead is actually standing up taking a photo. His name is Donald Rabb. He's also the creator of it. I'm also a Java champion, and everything that we are seeing right now is already on the GitHub repo. It's available for you all to take a look at it later. All the code that is there actually works. The project repo is should I upgrade my Java, and it's within my GitHub repositories under Nikhil Nanivadekar. So if you all want to take a photo, you can take a look at that. It's this. I actually learned this cool trick from my friend Rustam during their presentation, where you can just zoom that. It's pretty cool. Okay, so going back to this. All right, special thanks to my friends Billy Corando and Chandra Guntur, who not only helped me review as well as give content, but they also helped me prepare for this. So really thankful for that. With that, we are going to actually, so the way the talk is, I wrote the talk is I first look at measurements, performance data, then I look at features. I've been presenting for a while, and generally we see the metrics and everything towards the end, and till then we have lost focus and everything. So I thought, hey, why not first share the numbers and then do a feature comparison kind of a thing. So first one is JMH test. So JMH stands for Java Micro Benchmark Harness. I ran it on my teeny tiny 4-core i5 Intel laptop. So as always, your mileage may vary, so make sure you profile and test your application for your needs. The way I measured it is it was 3 forks with 5 warm-up iterations and 5 measurement iterations, and all the measurements that are reported are in operations per second. So higher the number, the better, because you want to have more operations per second. Please, I can't stress this enough, test, benchmark, and profile your own application. So how did I go about measuring it? So for me to measure, I had to first come up with a common usage pattern. I first tried to just see, hey, can I just construct list, map, set, and then see whether there's a performance difference, etc., etc. But then I realized hey, that's not indicative enough. I wanted to create use a common usage pattern for essentially to measure the performance implications, as well as how exactly the difference between different Java versions. So what I did is, being one of the leads of a collections framework helps you do is identify the patterns which are kind of heavy. One of the patterns which is heavy is actually Map.get as well as Map.put, and interestingly these are O1 operations. So they should be, we should be able to compare apples to apples. I measured it for string and integer, and of course the string comparisons with string itself and integer with integer itself. So let's look at the code for JMH test.put. So essentially it's a list of elements. It's just a list of integers which I go, and then in the map I just do put, and the key and the value is the same. I return the size so that the JVM is not doing some micro optimizations or some other funny stuff. So essentially, as you can see, it's the loop and the puts that are going on. One of the things is the map is not precise, so it has to you have to keep on resizing as the map grows. Same thing, a similar thing for the string dot put, where I'm just taking the integer, converting it to a string, and then putting it in a map. So fairly straightforward. So looking at the data, as you can, Is that clear enough? Okay, I think it's clear. All right, so as you can see, like I go from 1,000 elements to 100,000, and then I've measured JDK 8, 11, and 17. And you can see the figures in bold, the numbers in bold are actually for JDK 17 because they are the better performing ones because you're getting the highest ones. So interestingly, as you can see from JDK 8 to JDK 17, it's close to double the operations for small sizes like 1,000. And for JDK 11, I saw like there was a dip between 8 and 11 for smaller sizes. I just call that I just attributed it to some hysteresis or something like that because that was the only aberration, so to say. All the data is in operations per second and it's for throughput, so higher numbers the better. With that, let's actually look at string because string is a bit interesting where between from 1,000 to 25,000 elements, I actually saw that JDK 11 was performing better than 17, okay? And from 50,000 to 100,000, it was actually JDK 17. Now, interestingly, I actually spent a lot of time trying to figure out like, hey, what must be going wrong? And then even try to go through, hey, were there any changes happening between 11 and 17? What exactly happened? Because you can see clearly between 8 and 11 as well as 8 and 17, there is like performance gain. But it sort of did not make any sense why 11 to 17, 11 was performing better. Then sometimes you have to go back to your it's like Occam's razor, right? Like the most common solution is actually the real one, where this can be attributed to actual, again, hysteresis as well as the testbed setup, because I did run it through a few iterations and through different permutations, combinations, and then for some reason on my laptop this was the pattern, and I just wanted to show that pattern itself. But when I ran it on different machines, the trend was the same between 8 and 17. 17 always performed better, and 11 and 17 were comparable, with 17 being a bit better as well. So again, all data is in operations per second. It's for throughput, so higher numbers the better. Now let's look at Map.get code. So essentially similar to how I did for Map.put, where I had a list of elements, went through it, and ended up putting them. For get, I did the other way around, where I had pre-populated the map and then went through the list of elements and then just kept on calling get, because now I definitely know it exists, and then measured the performance for that. Now interestingly, similar to the map.put for integer, JDK 17 is performing much better. For 25,000, again, that's a blip. It's a comparable blip between 6,900 and 6,700 kind of a thing, and this also is attributed to test setup hysteresis. For JMH tests string of map.get for string, again, this was the exact same pattern that we saw in map.put for string, where from 1,000 to 25,000, JDK 11 was performing slightly better, and you can see it's ever so slightly compared to 17. And if you really look at all the changes that have gone in for string itself between 11 and 17, they're not that radical. So this and again, when I actually dive deep to figure out what exactly is going on, it kind of what do you say, confirm my hypothesis that it was something wrong with the actual test setup itself. So with that, we are going to switch from performance tests to memory tests. Again, similar to performance tests, while measuring memory, I was trying to figure out how to actually do that. I did a lot of trial and error to create a test bed such that it would actually be indicative enough of what exactly is going on, to the fact with tested a few frameworks to actually identify if the data structures themselves are using up different memory or they have different memory characteristics between different JDK versions. Instead of that, after all that failed, I was like, all right, let's just create a trivial program where we'll have a few for loops, and the JDK already gives you memory measurements, where it's use memory is equal to total memory minus free memory, because you have already method handles for total memory and free memory. Of course, because it's memory consumption, so smaller numbers are better. I've used the same setup as before, and again, please profile your application. Your mileage may vary because each use case is different. So let's actually look at the code. It's fairly straightforward. I made a map, a list, and a set, and then I just iterated it, over and over again. I did 5 iterations, and just tried to create like big enough data structures, and we'll see the performance measurements. For representation, only the output of the 5th measurement is printed, because otherwise it would be very difficult to show it. But all this code is available on GitHub, and you can literally check it out and like run, and it will start printing. So looking at the memory usage, as you can see, the bold ones are the better numbers. So in this case, JDK 17 performs consistently better, and for like 1 million, you can see like the difference is like by about 70 KB. So I think that's fairly negligible. Again, we can attribute it to testbed setup, but I did run this a few times, as well as I used the profiler as well. So I think these numbers are like indicative enough of what's going on. And you can see between, like, if you want to like draw patterns, then actually think about, even if you upgrade from JDK 8 to 11 for, let's say, a size of 10, you're still going to save like a lot of memory. And the same thing will be for like a size of 1 million, right? Now 11 to 17, you're still like saving more memory. So again, if you look at the pattern between 8, 11 and 17, like you are seeing those incremental benefits. Again, like I said before, the lower numbers, it is better. Just to summarize, JDK 17 consistently performed better in this than 8 as well as 11 for map.put and get in terms of integers. 17 consistently performed better for large sizes of put and get for strings, as well as it consistently used less memory in whatever the example indicative code that was written. Yes, Chal? Yes, it was the same GC. So yeah, good question. I'll update the slides with that. Yeah. All right. So those were by numbers. So as you can see, at least from a performance as well as memory perspective, it makes sense for us to upgrade from 8 to 17, right? But now it's not just that. Like, it's also the features. And the way I've illustrated the features and covered them are essentially the main ones, which are in general availability. I'm not considering previews, so you will see in parentheses is when it actually went to GA. Now some folks will say that like, hey, JDK 8 is like so old, but why are you even covering stuff which has come in JDK 10, like why don't you just start from 11 onwards? Eventually I will, when actually we have like, it's kind of my warm-up ramp, like as I'm like getting into from 8, 11, 17 kind of a thing. So, but with that, like what is var? So var is nothing but a local variable type inference, where instead of you having to denote your types, you can let the compiler infer the types, and then you so instead of map string, you can just update it to var. There are a few caveats to it. It can only be used for local variables which have an explicit initialization. So what that essentially means is code like that, you can verify it. Basically, you can change that map instead of writing the type map string, it can be replaced with var. Now a few things to pay attention, and this is something that it's super, because you all might start like just saying that, hey, we are going to replace everything with var. Again, up to you. I personally prefer just writing the types other than when I'm presenting, because it's easier and it makes it worse. But essentially, it cannot be initialized to null. So that's important. So you can't say var with var equal to null. It cannot be used to assign lambda expressions. So you can't have a lambda expression p of var. As well as just the personal preference and recommendation, avoid using var with polymorphic code. And the reason for that is when you're using polymorphic code, if you're not showing the types explicitly, you're just like doing it like with a var. folks who are going to read your code down the line, it becomes difficult, and then it also becomes difficult to debug. So while it is more convenient to quickly write it, you also want to pay attention to that. With that, next one, and if folks were in the previous talk as well, where Jose like went through, Amber, Loom, and Valhalla, this might be familiar, but I'll go through again. Essentially, from JDK 14, we started to get like updated switch statements, and the reason why I personally like it is because I use switch statements quite often, and prior to JDK 14, it was very tedious to write it, and we'll actually see the code what I mean by it. So the changes that have happened is now a switch statement can be used to actually yield a value. All right, it can contain the case statement in the switch case. The case statement can contain multiple values separated by commas. This actually helps in writing tensor code. A new restricted identifier was introduced in terms of yield. So essentially, what yield does is it allows you to use switch case with code blocks, and we'll see what that means in a second with code. Also, starting JDK 14, switch can be used for enums, and with all of these changes, a few a few constraints, or rather like few cool things in my opinion were introduced. Is switch expressions have to be exhaustive, and we'll also see what exhaustive means, and switch expression must yield a value or throw an exception, because the expression needs to evaluate to something. That's the reason why it needs to yield to a value, or it needs to throw an exception. So let's look at how it was pre JDK 14. So again, simple code where you get the month number and you want to identify which quarter it is. So 1 to 3 is Q1, 4, 5, 6 Q2, 7, 8, 9 is Q3, and 10, 11, 12 is Q4. So now if you see, all of this can actually be collapsed, but because of the old style of switch statements, we have to have that much redundancy, and we have to go on writing the same thing over and over again. Now with the new way, all that code can just be collapsed into pretty much 5 lines, right? And this is pretty neat, because it's also much more readable. Also, you're not writing the same thing over and over again. And this is also another thing is important is now you can only make change in one place, and then all Q1 values will benefit from it, instead of you forgetting or making sure your unit tests catch it, right? The other aspect of things is you can also so if you see the first variant is where we just return switch, right? The second one is you can actually, now that expression can be stored in a variable, and then you can return that variable. So just 2 different forms of doing it, and now it's allowed. The next one is to actually see it with yield syntax. Now the reason why yield was introduced is because now if you don't have code blocks where, let's say only for the last quarter we want to say, hey, yay, last quarter, the new year is close by kind of a thing, then it actually allows you to do that, right? But because once you get in the code block, that code block needs to yield a value. That's why you have that yield Q4, okay? And the default is not a month and year. But now, because like I mentioned before, switch statements can now be created with enums, it actually makes it super cool, because now let's say I have an enum of months, Jan to December, right? And remember, the switch statements, switch expressions need to be exhaustive. So what's going to happen is you have switch of month, and now the switch case is on the enum. Because it's on the enum, you know which all values of the enums are possible, right? Hence, you don't need a default clause over there, right? You don't need a default statement. And this helps us actually write bug-free code as well, because now let's say, I don't think this will happen, but let's say a 13th month was introduced, right? If a 13th month was introduced, by default it would have either thrown an exception or whatever the default thing is. But now this will be caught at compile time. You will actually get a compiler error to say that hey, it's not exhaustive, you have to cover that. And then maybe we'll have a case 13th month is why, right? That might be the response. But essentially that's the whole idea of making switch, the updated switch case statements with enums and making them exhaustive, all right? With that, next one is text blocks. So prior to JDK 15, we had to essentially deal with non-maintainable, long and tedious way of just writing strings. Basically, it constituted of a number of plus signs, like addition signs, as well as trying to figure out where what goes, especially for JSONs and everything. Like you have to figure out how to escape them. Just for an example, the old style of this is JSON. You have to figure out how do you escape the /n, how do you escape the commas, like how do you escape like the actual double quotes, etc., right? Now, interestingly, I'm a big fan of IntelliJ IDEA. I'm also presenting using IntelliJ IDEA. So IntelliJ IDEA has something called as code fragments, where for a particular piece of code, you can actually inject a code fragment, and then you can type it like regularly, and IntelliJ will figure out how to JSONify it and everything. So I mean, there were some workarounds as well, but essentially this was tedious and not readable, hence not maintainable as well. With the text block new style, all of that thing is just replaced with 3 double quotes. So 3 double quotes indicate that the text block is starting, and then the ending 3 double quotes indicate that the text block is ending. Within that is it's up to you, and you basically type out a formatted text block, like it's a fully formatted string. Java figures out how to escape the double quotes and everything. Now, because this is just an alternate expression, everything that applies to a string also applies to text blocks, okay? You're not getting like a different kind of a string, only the representation. So only the way you write, type code is changing, like nothing other than that. Now, folks will say, hey Nikhil, but this is good when you know what the variables are. What do you do when you know when the values are? What do you do if you need to format, you need to basically inject a variable? In that case, they introduced a formatted syntax where as you can see, you can put the placeholders like %s, %d, like the standard placeholders, and then use the dot formatted method on it, and then pass in the values, and then they will be taken care of at runtime, right? The next one is I think I'm doing well on time. So the next one is helpful null pointer exceptions. This is kind of cool. And yesterday I think I was talking to a few folks in the hallway, and they said this is their one of their favorite upgrades in Java. And then I said that the very first production issue that I caused was due to a null pointer exception, because I had forgotten to say if something equal to null, and then handle that case. I hope I'm not the only one who has to deal with null pointers. I presume it's pretty much all of us. So and I can see some nodding heads as well as some laughs. So yeah, I think all of us can empathize. Now, prior to Java 14, it was difficult to isolate NPEs in chain method calls. So if you had one method call another, it was very difficult to find out where exactly the source of the null pointer was. From Java 14 onwards, the null pointer exception actually prints out a detailed message on the cause of the NPE. A few things to note is it only prints out that helpful message only when the JVM throws an NPE. If let's say you have a case and then you're throwing throw new null pointer exception, then it won't print, then it's your responsibility to put that message. All right, so let's look at the old style of code. So let's say I have a person object, it takes first name, last name, and the null is an address field, we'll see in a second. And then as you can see, address is null, but essentially all I get to see is that hey, there's a null pointer exception. And like I said, all of this code is available on GitHub. You can download it, you can run it. When we see this in our logs, we see, okay, this is the line. Now I have to go and sleuth my way around to actually identify whether the address is null, whether the city is null, or for some reason toString is throwing null, right? So or sorry, the person itself is null. Now essentially, and this is presuming that you don't know the first line of person equal to something, right? With the new helpful null pointer exceptions, you actually get to see a detailed message. So now let's look at what it means. So again, the same line of code, Nikhil and null, but over here you can see that hey, it cannot invoke .city. So it cannot invoke .city because the return value of .address is null. So that way it tells me that like, hey, this address is null, right? Like this, the return of this is null. So go fix that, right? Now similar, to extend the same thing, because now it's an object within an object, to let's say now my address is not null, but my city is null. Similarly, it will also print out that like, hey, it cannot invoke string dot to lowercase because address.city is null. So I know that like this is the one that is throwing the null pointer exception, right? And that's pretty cool, and that's very helpful for us to do. A few things to note over here is, because of the detailed messages that are printed, you have to be super careful of what will be printed in the logs, right? Because let's say some bad actors or something like get hold of your logs, you don't want to have like sensitive variable names or sensitive method names or something like that out there. So you just need to take that much precaution. Where like, you know, with this convenience, also the flip side of responsibility comes with it. So just remember that. Next up is pattern matching. And it was introduced first in JDK 16, and if you all saw Jose's presentation, then he did cover quite a bit of pattern matching, and there are improvements which are going on in the JDK itself. So like, you know, what I'm showing you is pretty much the naive state, and more things are coming. So like down the line, you'll see, you know, these patterns being updated over and over again. So essentially, what pattern matching does is it is sort of Java starting to support patterns like, you know, of variables for its brevity as well as for safety. Languages like C# and Haskell already do it, and it's as developers, we, you know, all of us like love casting, right? I say it a little bit sarcastically, but essentially casting is error prone, right? It is also you know, difficult to maintain, and so this is sort of Java's attempt to also, you know, help us with that. So if we look at the old style of code, essentially I have a bunch of if statements where in case my input is a string, the instance of a string, then do something. If it's an instance of an integer, do something, so on and so forth. Now with the new way of pattern matching, what ends up happening is like you basically can just write this, right? If the input is an instance of a string, I can put it in the a string variable, right? And what Java lets you do is the a string variable, the scope of it is only this block. It's not going to go beyond that. All right, and this actually helps you, because now you don't have to worry about the error prone casting. Like your instance check itself is where you're defining your variable. You also don't have to worry about leaking your variables beyond your scope as well, right? Because now you'll start getting compiler errors because you won't have that beyond the scope, right? I want to pause for a couple of minutes for any questions if you have, while I take a sip of water. Any other question? Right, I'm just going to assume I'm doing a terrific job, and that's why no one has any question. Okay, going next to records. So records were introduced in JDK 16. Essentially, prior to records, we all you know, used to model data in Java just by using classes, and we used to call them you know, POJOs as well, like plain old Java objects. And essentially in the POJOs you would have like, you know, your sort of like holder variables or your member variables, which would essentially just hold data. We had a few you know, libraries like Lombok or something come to like sort of reduce the amount of boilerplate code that we had to write, but essentially they were, you know, they were not like available as a part of the JDK itself, right? Like we had to write a ton of boilerplate code like getters, setters, constructors, toString, equals, hash code, etc., right? With JDK 16, we got records, and with records, we got a few things, and we'll look at the example. So a few things to note is the fields in records are private final. All right, they're shallow immutable, and shallow immutability is a concept, and you know, we can look at that if we have time. But you cannot declare instance fields with records. With records, you get the default implementation of the accessors, so the getters, the hash code, the equals, and toStrings. It's automatically generated. However, some folks like to have more control, or some folks like to have their own custom implementations for this auto-generated code. You can override these default implementation. That's allowed. You can also write custom method definitions in records. So it still gives you the flexibility of like, you know, the Java objects that you had before. All right. So let's actually look at the old style where person non-record, you have private final, first name, last name, and then I've hidden the, I didn't type out the constructors or the accessors just for like, you know, otherwise this class would be long. It's essentially whenever I used, you know, whenever I wrote code like prior to having records, like I just used to use IntelliJ to, you know, auto-generate them, because you just press Alt insert and you can get it done for you. With records, all of this kind of changes into just, you know, with the new keyword record, that's the indication, and then you pass in your variable name. So like string, first name, string, last name. By default, string is private final, sorry, by default, because it's a record, the first name and last name becomes private final. And then if I want my own method definition, which is get full name, I can write that. It compiles, it works, there are tests around it. Also, if I want to override my toString implementation, I can do that as well. But the getters as well as the constructors and equals and hash codes, that is already, you know, automatically generated. So we don't have to do that. All right. So the next one is sealed classes, and this is actually one of my favorite new addition to the JDK, because as a library developer, presumably when all of us like upgrade to 17, it is going to help us like, you know, start protecting the hierarchy of pretty much our like, you know, collections, and that is super important, because that way we are not leaking in implementation level detail to like users, and it also helps you iterate and you know, move faster as well. So the whole intention of sealed classes was to provide a fine-grained inheritance control in Java. Because prior to that, like we had kind of a quasi control where you could have package private, you could have protected, but the level of inheritance control that now sealed classes give you was not there before that. Before sealed classes, every non-final class could be extended by any number of classes, like you had absolutely no control over it. So what we did, what the JDK did was, they introduced sealed classes, and with sealed classes, they actually had, they introduced sealed and non-sealed as two, you know, keywords, and then permits as another one. So basically what a sealed means is, like the keyword sealed essentially tells you, tells the JDK that it can only extend or it can only be implemented by classes that are permitted to do so. And that's where the permits clause comes. The non-sealed ones are essentially open for all. They can, you can essentially use it to open just a part of the hierarchy without worrying about like exposing rest of it. A few things that I found out while I was, you know, writing the talk is, if subclasses are in different files but they're in the same module or package, then you have to use permits to define the subclasses that may extend the sealed classes. It was kind of a long way of saying it, that like in case subclasses are in the same file as the sealed superclass, like you don't need to use the permits clause. And I learned that like while I was, like I said, the code is all working and everything, and like my unit tests were still passing when they shouldn't pass, and that's when I was like, okay, let me dig deep a little bit and understand. That's when I found out this last one, that like, hey, if they're in the same class, then if they're in the same file, sorry, then you don't need the permits clause. Like it basically gets open for everyone. So let's look at the hierarchy diagram. Essentially, I have my interface user. It's sealed. The dashed line means sealed. The dotted line means you know, non-sealed, and the solid line means final. So I have an interface user. It's a sealed interface. It has three you know, other implementations, or some of them are interfaces as well. So you've got owner, admin, resident. Admin, owner is a final class. Admin is a sealed class, and resident is a non-sealed class. So as you can see, resident opens it up for day guests as well as overnight guests, and you can have as many as you want. Admin, on the other hand, only permits super admin, and we'll look at the code in a second. It does not permit temporary admin. So even though temporary admin wants to become an admin, they don't get to be. So it's kind of that. So if we look at the actual interface, this is how it is. Essentially, public sealed interface user, it permits the three that we saw right now: owner, admin, resident. And I just created a default method called login just for testing. Now, if we look at the sealed interface hierarchy, so if you remember in like 2 slides before this, owner was my basically my final class, admin was the sealed class, the dashed lines, and resident was the non-sealed class, so dotted lines, right? And so if we look at it, then if we just take admin, then because admin is the sealed class, it is implementing user, but it's only permitting super admin, okay? Because of that, this actually works. This test passes, it works and everything. However, because temp admin is not listed over here, so the temp admin is not permitted over here, hence it does not compile. So it's not a runtime exception, it's actually a compile time error. It doesn't even let you compile, and that's pretty cool, because you don't have to worry about like getting surprises down the line. In case of the non-sealed, the resident is a non-sealed class, so dotted line if you remember. Hence, it can it doesn't need a permits clause. It can be extended by as many classes as they want. So it essentially opens that side of the hierarchy. So you can get through the resident one instead of the temp one, right? We are almost coming towards the end. So in addition to adding stuff to the JDK, there are a few things that were removed as well. One of them was the Nashon engine. So Nashon was like the scripting engine that came with JDK. It actually spun off as its own open JDK project, and it's maintained separately. And this is pretty cool. Like you can actually put it as your Maven dependency instead of it being shipped out of JDK itself. The CMS garbage collector that was removed in JDK 14, it had a good run for a few years, and I think it was time with like all other GCs coming up. On 17, as a part of JDK 17, in addition to the sealed classes, they also started strongly encapsulating the JDK internals. So now, things that used to leak, like the implementation level details that should not be exposed to users, they started getting sealed. And there were a few more deprecations, but these were the 3 interesting ones that I thought I should call out. Lastly, we are not going to go too deep in the garbage collectors, but I just thought it was worth a mention that these are the ones that now are available. Each one of them has different uses and different reasons, different life cycle, etc., etc. The detailed notes are available on the GitHub repo. Also, the GC aspect of things is a completely deep area for talks as well as research, and there are enough out there in the community. So lastly, as takeaways, with JDK 17, you're getting performance improvements, you're getting new features. Upgrade to JDK 17. So like I said before, the first 10 seconds of the talk was essentially upgrade. Yes, the answer is, should I upgrade my Java? Yes. Now we know why of it as well. If you're still on JDK 8, you might just want to skip 11 and go directly to 17. And what I mean by that is you will need to do incremental work to go from 8 to 11, but the delta from 11 to 17 is small enough that you might just want to scope it and get it done together. JDK 17 is now more than 18 months old. It was released in September 2021. JDK 21 is about to be released this year, which will be the next LTS version, so to say. JDK 20 is already released, and essentially, change is the one constant in our lives. So you have to embrace the future. So don't wait for your upgrade. With that, thanks a lot for being a great audience. If you have any questions, happy to take them. Thank you.